Okay, our presenters today are Dr. Pei-Sung Lin and Dr. Achilles Kotelis. Dr. Pei-Sung Lin is the Program Director of ITS Traffic Operations and Safety at CUTR. He obtained his master's degree from the University of Texas at Austin and doctoral degree from the University of Florida. Currently, he serves as the chair of the Intelligent Traffic Signal Operation Committee at the Institute of Transportation Engineers. He has 21 years of work experience and has published and presented numerous papers in national and international conferences. Dr. Kotelis is a research associate in the ITS Traffic Operations and Safety Program at CUTR. He earned his master and PhD degrees from the University of South Florida. His dissertation was entitled Operational Evaluation of Advanced Safety Enhancement Devices, Rearview Video System, based on a project funded by the FHWA and FDOT. He received the George Bosch Transportation Scholarship and was named Student of the Year from TBITE during his doctoral study. He has co-authored 4 papers and authored 3 papers presented and published at the TRV annual meeting, ITS World Congress, and AATT conferences. And Dr. Lin, I will go ahead and turn it over to you.
Good afternoon, everyone. I'm very great to have this great opportunity to present you with our NCTR project, and it is sponsored by FDOT as well as Federal Transit Administrations. And let me give you a quick background about the time frame for this project. It started in January 2009, and it was completed in March 2010. And as we all experience that, we know that transit buses, when they may experience side collisions, and it's possible during the lane changes or when they try to merge from the stop bay to the major roadway, or maybe during the turning. And when we look at that, we found out that one of the major factors contributing to these side collisions is because there's a side blind zone area. As you know that when transit bus is not like a passenger car, it's long, and there's a certain part of the on both sides the driver cannot see that. And when we look at the if there's a crash, and we found out if the bus driver at fault, and one of the major reasons is just because they cannot see other vehicles on their side. And there are many studies look at different way to see what will be the better device to provide that and to reduce crashes. And one of them is a sensor system. And there's a particular study conducted by FTA, Federal Transit Administrations, and they have a sensor around all the vehicles, around the bus, and the results show that it do provide a warning system, and they will have a sound to warn the driver. However, they found out that it's not detect the object on the side all the time, so they do not provide 100% of time of detections. So if we look at the crash data, and this slide show you based on first, as you can see on the top, it's based on the National Transit Database, the crashes in 2002. And from this particular table, you can see that the initial point of impact during a crash, and there's a 46% is either on the left side or the right side of the bus. And among these side crashes, and 14% fatal crashes, and 36 involving with injuries. And so that you can see the crash at the side of the bus is the majority. And the next table is that we try to compare the collisions involved with the transit bus and compare with all the crash occur in all modes. And from here, you can see collision with the vehicles. And sideswipe is 33% for transit buses. And this is another evidence to show you how important for transit driver to see the vehicles or pedestrians, other objects on their side. And we'll go to the next slide. And based on the information and the needs, and our research team come up with the methodology, and it is shown on this slide. So first, we would like to do is we like to conduct literature review and compare the existing meter system, and also compare with the sensor system, and there's a camera-based system. We try to compare those to see what's pro and con, and how we can improve the system to better to eliminate the blind zone area. And after the literature review, we perform we call volumetric measurements, and basically we know that based on the no zone area on just the frame meter, there's a certain place the driver cannot see, and not just one dimension, 2 dimension. We like to look at a 3 dimension, so that's why it is called volumetrics. So it's a volume. There's a certain part of no zone in the volume, and so we use the area for the frame meter as a baseline, and we try to test it out. Okay, if we use the convex meter, what's the percentage of no zone area can the volume can be reduced, and then we compare with the camera system, and so this will give a good comparison. And the next is we design and perform control driving tests, and to evaluate the camera-based system. And then you may have a question why we like to perform this test. And the reason is because this is a really very new concept, and we don't have the crash data based on the side view cameras. And try to test this out. We like to have a control environment, so we'll be able to control, say, under different scenario, and to test it out, whether to compare and evaluate our camera-based system. And then after that, because we know it's very important that the transit bus driver, their feedback is crucial, because any new devices, if the user does not like that, or they have problem with using them, or they don't like to change to use them, then we need to see how we can improve. And it's also very important that with their support on the system, and the system can be used in the future and widespread throughout the transit agencies, maybe as well as trucking industries. So based on the literature review, and we found out that the current meter system basically is the frame meter plus the convex meter, and they still leave a big blind zone area around the vehicles. And the sensor system will, from time to time, they will provide, they will give some false alarm, and it becomes distracted to the drivers, and they cannot provide 100% reliability all the time. And there's some study use the camera system as use machine vision, basically try to use the camera, the image, try to detect there's the vehicle around the transit buses. And but so far they are very limited of study on the side view camera, and there's several that are small on the commercial truck. And for transit buses, and this study is kind of like a pilot. It's a pioneer. It's a study we conducted, and we learned a lot from this the pilot study. So the next slide I'll give you a quick overview about the meter field of view. And so basically, based on the meter, either on both sides, on the left and right, and as you can see that the area here on both sides, this is the frame meter field of view, and on both sides a little bit dark, brighter. The gray area is a field of view for convex meters. And as you can see, these are the standard meters for transit buses, and we got the frame meter on the top and the convex meter under that. And this I just try to show you the one I mentioned earlier about the sensor-based system. And so basically, they have a sensor kind of around all the vehicles, and to provide detection about the vehicle around them. And so the first measure we conduct is, as I mentioned earlier, is we try to measure when we use the convex meter, regular angle length of the camera-based system, or we use a wide angle length. We try to compare what's the percentage of reduction of the no zone area in the 3D dimension. So as you can see from the table here, and the frame meter basically is we use that as a baseline, and so there's no reduction on the no zone area. But when we use a convex meter, the convex meter under the frame meter, and you can see that there's a 40.8% reduction on the left side of the transit buses, and on the right side there's a 35.1% reduction. And when we use the regular angle length, you see a much bigger reduction. It's a 64.4% on both sides. And when we use wide angle length, it can reduce up to 100%. This slide just try to show you the camera and the monitor we installed during our study. And as you see on this particular picture, you can see the camera is a CUTR Web bus, and we install the camera on the top. It's a little bit higher on the bus and look down. And for the lower floor bus, the camera is installed under the meter. And the picture on the bottom, as you can see, this is the monitor, and on both sides. And this is a 7-inch monitors. And during the test, we cover the meter. And so the next we'll move to control driving test. And let me first describe what's our objective. So the first objective is we try to test whether the driver can perceive the distance similar like the meter and cameras. Basically, we ask the driver to drive the vehicles, and we design a scenario and try to see whether the transit driver can use the camera alone to drive that and compare to the meter. And the second is we're going to try try to test whether the camera system can help the transit driver to eliminate the blind zone area. And the third objective is we try to examine the distance perception, because this is very important. Whether the driver they can perceive a similar distance using the cameras or we call side view system and compare to the mirror. And finally, is we try to collect the feedback from the transit driver, to see, how do they feel about using the side view camera system, and how can we enhance the mirror or camera system in the future. And there are a total of 28 participant bus driver for this control driving test. And the first I look at a picture on this is a facility near University of South Florida, and we said it's a very large area, and it's pavement on this area. So we actually it's a very good environment location for control driving test. There's no other vehicle here. As far as the transit driver participating in this study, their age, the age is mixed, from under 25 to more than 50 years old. And the experience of driving on transit buses from half a year to 52 years. And two types of transit bus we use for this study. One is we call CUTR, is kind of the shuttle bus. And the other one is a low-floor bus, as you can see here. Another is about experience. 11 drivers out of 28 drivers, they have previous experience with the rear view video system, and so they are more familiar with the video system. And so the next, I'm going to turn this to Achilles to talk about the detail about the control driving test, as well as the survey we conducted and what are the results from the survey. So Achilles.
Thank you, Dr. Lin. So good afternoon, everyone. I'm going to continue with the control driving test details. We started first, obviously, as Dr. Lin said, this was a closed course, so no other vehicles were involved. We had set up this course that you see in the slide right now. We had the drivers driving around twice this loop just to get familiar with the system. Some of them obviously was the first time they had experienced this kind of system. So we want them to become familiar and see how much they could see and what they could see. When the drivers were driving around, the course was set up with transit cones, as you can see on the right side in the pictures. Then after that, and after they felt comfortable, we started doing the two driving maneuvers we explained before. And then finally we did the test under study conditions. Basically, the bus was stopped, and I will explain more later on about the test. So the first maneuver, what we had set up was a 3-lane section, let's say, and we had the bus in the middle lane. And a second car driving either to the left or to the right. We did both sides. And we asked the drivers to tell us what was the last moment they would actually change lanes in front of the oncoming vehicle. Now, the bus was driving at a constant speed of about 15 miles an hour. And the vehicle started with the bus, and it was slowly accelerating as to pass the bus, let's say next to the bus, as you can see on the two first pictures. So let's say this vehicle here was going to pass right next to the bus, and on this side it was going to pass on the right side. So as the vehicle was coming behind the bus, we asked the drivers to let us know when was the last moment they would actually change lanes in front of the vehicle. No lane change was permitted, obviously, for safety reasons. We didn't want to have any crashes involved. But we found a way so that they could let us know when that would happen. And the idea was to be able to capture the distance between the vehicle and the bus when that moment was happening. So as I'm going to explain later on how we did that, when the driver told us right now I would change lanes in front of the car, we measured the distance. We measured this distance between the vehicle and the bus. The idea of this test was to be able to see, basically, as the objective says here, see if the distance and the speed of the vehicle is perceived correctly using the camera system versus using the mirror. So we did this test 4 times, 2 times, 1 for each side with the mirrors, and then 2 times, 1 for each side with the camera system. The order of the maneuvers was random, so each driver had to separate a different setup. And that's how we did this maneuver. I will present later the results. The second maneuver was geared towards helping the drivers understand the limitations of the mirrors and how well the cameras cover those limitations. Basically, we're talking about the side blind view. So what you see in this picture, the shaded area is the field of view of the convex mirror. So that means that the drivers can actually see in that area. Now we placed the vehicle on the lane adjacent to the bus, so it wasn't right next to them. So assuming the scenario where you have a 3-lane section again, and both the vehicle and the bus were actually planning to merge in the center lane. If the vehicle is located right where it is right now, as you can see, it is questionable whether the driver will be able to actually see the car. And if they both change lanes, and let's say even if the vehicle's driver is not attentive and they both change lanes at the same time, of course you're going to have a sideswipe crash. And in this case, we are placing the vehicle not right next to the bus because obviously the driver should be able to see there. Although there is still a gap, as you can see, all this area here is still, this is the blind zone we're talking about. So if the driver door is located to the lane next to the adjacent lane, then the problem becomes bigger because there is completely in the blind zone. So that's what we're trying to do. Now, what we did here, we had the bus again drive at 50 miles an hour, and the vehicle increasing speed from behind the bus to pass the bus. We asked the drivers to tell us when was the last moment they were able to see the vehicle in their mirror. And we took a picture at that point using the camera system so that we are able to show that with the camera system you can still see the vehicle. And I'll show the results later on. The last test was, as I said, a static test. So we had the bus stopped. We had the researcher stand in a specific location, both left and behind the bus. So we used 2 dimensions, looking for 2 dimensions, and we did this for both sides, left and right. And we asked the drivers to tell us where they thought the person was standing, how far behind the bus. So each driver did respond, and they told us the 2 distances are shown here. So they told us how far behind the bus they thought the person was standing and how far to the left or to the right. We did this for this. So we actually placed the person in both left and right sides. The idea behind this test was to be able to capture how well the drivers can see and perceive distances in static conditions. And again, we did the test twice, once with the mirrors and the second with the camera, to be able to see if they can understand the distance correctly or similarly to the mirrors. During the test, we had to be able to collect our data. We had, as you can see on the left image, basically shows the cameras we had. So we had a total of 4 cameras installed. One was the left side camera, the side camera. This was visible to the driver via a monitor. What you can see on the right side is also the schematic. So camera number 1 was shown in this monitor here that I'm showing right now. Then camera number 2 was the right side camera. It was located, as Dr. Lin said, close to on the wall of the bus in the far in front. And we had a monitor placed on the upper right corner of the bus trying to show the camera. Camera number 3 was a rear view camera that we used for it was placed on the backs, and this was used to collect the data for the distance measurement, and I'll explain later how we did that. And we had a 4th camera which was placed right here. It was looking at the driver, and we were trying to see, it collected 2 kind of data. One was to be able to see where the driver was looking at, so which mirror or camera the driver was looking at, and also be able to capture the moment they would tell us when they would change lanes in the first maneuver. I'll explain how we did that in a second. These are the views of the cameras. So on the left side here, you're going to see this is the left and this is the right side camera view as the drivers were looking at it. This is the rear view camera, and we use this to collect our distance data. And this is a snapshot of the camera looking at the driver. As you can see, we have the driver here, and then we had placed a push button with an LED light. We asked the drivers to push this button so this light would go on, and we would know exactly when they thought, as I said in maneuver 1, we asked them to change lanes or tell us when they would change lanes in front of the oncoming vehicle. So instead of changing lanes, they just pushed that button. So the light came on, and at that point we had a snapshot of the camera, of the rear camera taken, as you can see on the left. Now, the way we measure the distance, we previously had actually made a scale. So as you can see, we placed the scale on the ground. And this is a schematic here. The camera obviously, so this point here, let's say at 20 feet behind the bus, is this point right here. It's the same point as where you can first see the first line. So we knew exactly, let's say, how far behind, because of the scale, the car was. So using this, when we took the snapshot of the car, when the driver told us that I would actually change lanes right now, as you can see, we made this scale superimposed on the picture. So we could measure, let's say at this point, this vehicle is located at about 30 feet behind the bus. So that's how we measure the distances when the bus was driving. Otherwise, we wouldn't be able to do it. So this is the results of the first maneuver. Just to recap, so the maneuver was basically asking the drivers to tell us when was the last moment they would change lanes in front of the oncoming vehicle, and we recorded the distance between the vehicle and the bus. The graphs here show the distances for all the drivers. Now you're going to see 2 different colors. The 2 colors represent the 2 sides of the bus, so left and right. The x-axis shows the number of the drivers. So for driver number 1, let's say his left and right were both the same. For driver number 2, his left and right response wasn't exactly the same. Here, as you can see, one is higher, one is lower. And this is the same for all of them. Now, the first graph shows the responses for the distances using the mirrors. And the bottom graph shows the distances, exactly the same thing, using the camera system. We also calculated, based on safe stopping distance, what was the minimum stopping distance safe enough to actually change lanes and not force if the vehicle, let's say, had to stop behind the bus, not to crash on the bus, it would need at about, I believe it's 32 feet here. So this line represents, let's say, the safe barrier where all the drivers that mention a distance lower than this. That means that they are probably taking a risk because they're leaving the car to come closer to the bus before they change lanes in front of it. And the drivers that are on top of this line, as we show here, these drivers here, they're being cautious, they're being safe, and they leave a big distance in front of between the vehicle and the bus, so that there's no, I guess, incident for potential crash. As you can see, the two graphs are fairly similar shaped. We didn't analyze one by one, but as you can see, the results show, and the line is obviously, this line here is the same line in both graphs. So this line is the same as this line. And you can see the results of the distances. We were pretty happy with this because it shows that drivers do, using the camera while in motion, were able to actually perceive the distance and the speed when the vehicle was coming behind them. And we do see some differentiation and some changes in some of the drivers. But obviously, with the limited data we have with 28 drivers, we cannot infer on very accurately. We will need to perform more tests to be able to actually say if they can perceive exactly the same as the mirrors, or better, or worse. The next result shows of the second maneuver. As I said, the picture shows, let's say, where the vehicle and the bus were. Again, this schematic here on the right side shows how it happened. So the results of this test, I can basically show you a picture. So this picture shows on the left side, this is the mirror of the bus, and you can see this is the flat mirror on the top, and this is the convex mirror at the bottom. Now at this point, the car is located right next to the bus. Now, and it's not visible even in the convex mirror. We all know that the flat mirror doesn't really help you with this situation. But even with the convex mirror that is pretty wide view, you can barely see the shadow of the vehicle right here. Now, at the same time where we have placed our camera, and that's pretty much where the camera should be, you can see the picture of the monitor of the side view camera here, and you can see very, very visible the vehicle right here. So this is what we're trying to show, that using the camera system, we can actually see and eliminate the blind zone that the mirrors leave behind. And the drivers were able to understand and see this difference, and I can say that they all like this. These are the results of the last test, the static test. What we show here is that the star represents where the person was actually standing, and as the legend says here, where you see M, it basically says where the drivers told us that the person was standing using the monitor, and C is where the people told us that the person was standing using the M is with the mirror, and C with the camera. Now you can see that many of them did miss it by a lot. We are not really, that's not important. What's important here is to be able to see the ones that actually overlap. So for example, these two here, the C and the M overlap. So that means that drivers were able to actually, the drivers were able to see say where the person was standing using the mirror and the camera similarly. And we perform a statistic test on this to be able to see if the two groups of distances are different, and statistically they are not significantly different. Now I want to mention that this is the statistic test, so somebody can tell me, well, but how about these ones out here? These are what we call outliers, and obviously you're going to have these things in any test you do. Like I said, this is a limited data test, but it's an initial proof of concept. So obviously, in order to be able to infer and say that the camera system is the same as the mirror, we would need more data, or a larger sample size. And the survey, we asked the drivers at the end. We had 8 questions before the test about how they think that the system is going to perform or what it is, and 60 questions after the test. The questions were dealing with the effectiveness of the mirror system in rain and night conditions, what they think about it, the limitations that it has. We asked them about their crash history in the past, again, sideswipe or side crashes, if they had any. We asked them about previous experience with the systems, with camera systems, because this is important. We also asked them to be able to tell us their perception about the system, how easy they think it was to use before and after, how much time it takes them to actually adopt and be able to drive. We asked them about what they think the system can help with bus safety, and just we also had it open for them to be able to tell us comments, give us feedback of the system, how we can make it better, and stuff like that. Now, this is not all the questions. Obviously, this is just a summary. Some of the questions replies, as you can see here. One question was, with the side view video system, are the side blind zones reduced or eliminated compared to conventional mirrors? So the answers you see here is before and after the test. And the 2 columns represent the 2 types of buses we used, the cutaway and the low floor. So as you can see, there is a majority of drivers before and after did say that they agree that the side view system eliminates or reduces the blind zones. I believe that after the test it was slightly more, and this was what we were looking for, to see how they changed their opinion. A second question I have here is, can a side view video system help drivers reduce side crashes by providing a better view? And you can see the responses before and after the test. And again, the majority of them, if I split the image in half here, this is agree and this is disagree, let's say. So if you count the numbers and you do the percentages, you're going to see that they are, the majority says that they can agree. Another questions we had was, with the side view video system, did you feel comfortable performing a lane change maneuver? And there you see their answers. And also, does the side view video system have the potential to help reduce side crashes during a lane change maneuver? And this is important because obviously the camera is going to help during a lane change maneuver most of all, because that's where the driver uses the mirror to actually see left and right of the bus and infer about the vehicle traffic around them. And a summary of the results here. The drivers did agree that the system reduces or eliminates the side blind zone compared to the mirrors. It also helps by providing a better view. In general, the system can improve bus safety. Also, some things that we asked with the drivers, they can actually observe late arriving passengers. Sometimes you have some passengers that they kind of miss the timing and they run after the bus has already left the stop. They said that sometimes you cannot really see them with the mirrors, and it might cause a conflict at a point where it's dangerous for the pedestrian, really. With the camera, because they can see wider, they can actually see them coming from far, larger distances. Drivers would like to have this system on the bus they drive every day. That was one of the questions we asked. They felt comfortable performing a lane change maneuver with the system, and the system can help reduce crashes during lane changes. Other benefits that came with the system was that we actually observed, and we knew this, but as you can see here, this is during nighttime. Now the cameras had infrared LEDs, and that's one of the good things about having such a system. What you can see here is at the same time we took a picture of the mirror and the system. It was during nightfall. It wasn't entirely dark yet, but as you can see outside using the mirror, you can see whatever you can see with the light that is outside. But with the camera system, because it has those infrared LEDs, it illuminates the area just like it's pretty much daytime. So everybody liked that because you can see much better, clearer, and more details using the camera system. Another thing that was observed was also the fact that during rain, because the droplets of the water go on both on the window and on the mirror, it becomes pretty difficult to actually use the mirrors, and we all are aware of that. We all drive. So here's a picture on the right side of the camera system, the monitor, what the driver could see. So because the surface area of the lens is so small, you can actually see better during rain conditions as well. Now, these two results were just an added benefit. We found we need to perform a little bit more tests to be able to actually say 100% or how often this happens, or what's the percentage of time that we can actually say during rain or night, during rain especially, the system is better than the mirrors. And the last benefit we also found was, as you can see here, this is a cutaway bus. The mirror extends quite a bit out of the side of the bus. And this is actually one of the problems that small transit agencies or agencies that use this kind of buses face, because this particular mirror doesn't meet the height requirements, and it's actually dangerous. It might hit a pedestrian. And we did have some instances where people were hit by a mirror like this. Using the camera, however, this is where we had placed the camera on this type of bus. The camera has a footprint of about, it extends out about 1 inch from the side of the bus. So obviously, it's not going to be a problem exactly wherever you place it along the side of the bus here. So that was an added benefit for that. And now, before I hand things over to Dr. Lin, I have a question for everybody, a poll question. Would like to ask you this, and if you could please answer this question. Okay, so it looks like a good majority seems to agree that the system is an enhancement to the mirrors. And we'll explain later what's our next steps, basically, when I hand it over to Dr. Lin. Thank you very much.
Thank you, Achilles. So at the end, I would like to provide you the summary of our findings. So the first one is, as you can see that through representation, the current mirror system do have a limitation, and they still leave a large blind zone area, and that contribute to crashes. And the second one is that in this control driving test, we use the aftermarket side view system, and all the tests we performed and demonstrate that the side view camera system do have that potential can eliminate 100% of the blind zones. And it depends on the camera used, and also the monitor and camera angles, several factors. And the third one is that the control driving test we did show that the most of the driver can perceive the similar distance, and this is, as we mentioned, is very important to implement the camera system, and in both static and dynamic conditions. The next finding we have is that from the driver survey, it confirmed that majority of transit driver participating in this study, they like the system. They agree the system can eliminate the blind zone and help reduce crashes. And as you can see from the before and after survey. And the last finding we have is the camera system can enhance the mirror and maybe potentially replace the mirror in the futures. In the next slide, I would like to just let you know what's our future work about this research. So based on the finding from the study we just conducted, the phase 2 was proposed. And so what we try to accomplish in the phase 2, the first is we like to investigate what would be the best setup and specification for the enhanced side view systems, such as where should we place the camera, what kind of monitor is better, should the size should be bigger, or how we place that. Should the right side monitor should be bigger than the left side because it's a little bit far away from the drivers. And the second part of our work is we try to see, because the mirror provide a good visual on both sides, and we all use that, and we are so used to it that to the mirror. And so how can we integrate the camera with the mirror and use the camera system as supplemental devices and go with the mirror and can provide an integrated system to help the drivers. And so we want to investigate that and produce a prototype and provide recommendation to Florida DOT transit offices. And the next one is that which we will work with the transit agencies in Florida, and we like to deploy the enhanced combined mirror and camera system, and to deploy that for a longer time to evaluate that, because from the driver control driving test we performed earlier, it's a very short period of time we did a test. But in order to see whether we can use this enhanced system in the future for transit agencies, we really need to do a much longer time of deployment to evaluate that. So that's the work we're going to perform very shortly. And finally is that based on the deployment with the enhanced mirror and camera systems, we would like to develop the specification for future integrated mirror camera system and for transit buses, and we'll provide this specification. So in the future, if the deployment is successful and demonstrate the effectiveness of this integrated system, and based on the specification, and this integrated system can be widely deployed in the future. And so this will conclude my our presentation. But at the end, I also want to take this opportunity to acknowledge our FDOT transit office, Erin Skippers and Victor Wiley, and thank you for their guidance through this research project.
Okay, great. Thank you very much, Dr. Lin and Achilles. Now we will move on to our question and answer portion of our webinar today. You can see the instructions here, like we went over earlier. If you have a question, just click on the Q&A, type in your question, click on the Ask, and then we will address your questions. Looks like we have one so far. The question is, did the sun have any effect on the ability to view the camera system? Just wondering if the drivers had any complaints on the ability of viewing the screens with glare, more so on the passenger side than the driver's side, since that is the farthest.
Yeah, I can. Basically, obviously the glare is one of the biggest issues that monitors face. We did have a couple of instances where the glare from the view was so much so that it was almost as a problem, I would say. But we basically saw that as if you were driving the bus and you actually hit the sun, it would pretty much present you the same problem. Now, the right side monitor, one of the things that we found when we asked the drivers also was that they would like it to be bigger in size. We used a 7-inch screen on both sides, and obviously the one on the right side is farther from the driver, so on the cutaway bus it wasn't that big of a problem, but for the low floor bus it was because the distance is greater. And like Dr. Lin said, one of the things that we're going to investigate later on is if we're able to bring the monitors closer to the driver or put them in a different setup, in a different place, perhaps even use one monitor to be able to present both screens. You can do that these days, maybe with a bigger screen. So those are one of the things that we're going to investigate in the future. For the test, I can say that we didn't have big problems. The drivers didn't complain, per se, about glare. But as I said, there was a couple of instances where the sound was located. It was creating a little bit of a glare on the monitors.
Yeah, I think this is a very good question, and that's also raised, I think, during our test. And as Achilles just mentioned, that that's why in the phase 2, and this is one of the potential issue we're going to investigate, and how to place the monitors, and maybe still on both sides. Maybe we can do on the landscaping setting, or maybe in the middle of the driver. So it really depends on the experiment we're going to do, and also we're going to work with the transit drivers, and to come up with what would be the best setup.
Okay, great, thank you. Just going back to our poll question that we asked, I know that there was at least 1 or 2 individuals that had disagreed. I'd be curious if you would like to participate and ask a question. We'd be glad to address that. One more question we had that came in here is, in Florida, with the humidity, do the cameras fog so that the view is out of focus?
Obviously, with all these technologies, there's always going to be some problems. Now, using a good camera, you don't have the fog problem. Now, I hope you mean that on the outside, because of the humidity, it's going to create, now, that can be treated the same as pretty much raining. Like I said, our experience has shown that that wasn't a problem. Of course, and it was actually better than the mirrors, where you have to actually go and clean the mirrors in case that happens. But we have to run more tests in order to be able to infer on, if the cameras are perfect or have certain limitations under certain conditions.
And do you have any experience with ice and snow and condensation?
Unfortunately, ice and snow, no. The previous studies we had searched in the literature review did have things to say about the ice and snow. Actually, if you're placing the cameras in areas where you have this problem, there are actually heating elements that can go in the camera housing that can help warm up the lens and melt any snow that there is. Obviously, the location of the cameras is going to play a role, and the lower they are on the road, the worse it is, because they can be covered with mud or any other particles. So that's again one of the things that we have to find out, if the location we actually place the cameras or where the manufacturers say you should put them is actually the best location for them to be.
Okay, great. Another question coming in is, I see the tests were performed on shorter buses. Have there been any tests performed on 35 to 40-foot buses or larger? And if so, were the findings better?
The 2 buses we used were both 30-foot buses, just different type. We didn't at this point have access to or did a test on a longer bus, but that is that's in the plan section of the second phase, as Dr. Lin said.
And in phase 2, we also are seeking for potential partnership with manufacturer, and work closely with FDOT transit office, and so it should be a very good research, and combine the research and cooperation from manufacturers.
Okay. Another question coming in smaller transit vehicles, 14-passenger paratransit vehicles, would this system seem more beneficial over the traditional mirror system, or would it simply be an added expense for these smaller vehicles?
When we started this project, actually one of the reasons behind the whole project was to see if we can produce a camera system, if we can use a camera system that would actually replace the mirrors, because it would basically have a better view. Now I know that we are far away behind before that is going to happen in the future, maybe. I would say that at this point it looks like an enhancement would be better. Because the technology is not there yet to be able to replace the mirrors and have a 100% foolproof system. Maybe in the near future, as technology becomes better and less expensive, that's going to happen. We already see in large trucks right now, manufacturers do have concept ideas where they replace the mirrors completely with cameras. But I would say that at this point, it looks like it's much better to be used as an enhancement on the mirrors. And as far as the cost, I wouldn't say that the cost is prohibitive. If somebody does a cost-benefit analysis on obviously the number of crashes they have, or even if they want only one crash, the cost of the system is not that great. That would be prohibiting to install.
Mm-hmm. I would like just add one more benefit of use additional the cameras. And as we know, for transit agencies, we a lot of time we got a different transit driver to use the same vehicles, and so there's a potential benefit of when we set up the camera and have a good adjustment, and the view will be the same no matter how the transit driver, either tall or short, or they need to adjust the meter all the time. But with the camera, you'll be able to get exactly the view you like to see.
Okay. I think we'll take one more question. For those of you still on the webinar, I'd like to remind you to stick around for the evaluation. We'll put that up in just a moment after this question. For those of you who did not get your question answered, I will be forwarding those to the presenters, and they will follow up with you directly via email, so you will get your questions answered. The last question we have is, I would think insurance agencies would be interested in your results. Did you have any contact with them?
I think at this time, we are still in the early stage of the experiments, and with the phase 2, after we conduct the phase 2, I think we probably can provide much clearer pictures and potential future deployment. And I believe at that time we'll be able to provide good information to everyone. And I think this is a insurance company will be very interested in doing that if this assistant will be able to reduce crashes and for transit buses, and definitely that would be a good benefit to use this system to reduce the insurance cost.
One thing I would like to add before we finish is that for the insurance, we have done previous projects with backup camera systems, and we did contact insurance companies to be able to see what they thought about it, if they were going to be able to give maybe a discount, or how they saw the whole addition of the backup camera system. What we got out of it was that the calculation of the rate is such a complicated formula, and obviously a secret for every company, that it would need a system to be proven to work and reduce crashes before they would actually consider adding it in their formula as a discount, let's say. So that being said, though, we do see now in the auto industry more and more devices and enhancements added on, and we do see insurance responding with some discounts on your premium for that. So I wouldn't expect that in the future. I'm expecting to see something happening like that for transit agencies as well using the system.
Okay, once again, thank you, Pei-Sung and Achilles, for presenting today. As a reminder, our next webinar is on June 2nd. We'll be presenting on transit improvements from the Urban Partnership Agreement Program with Brian Pissarro. And if you could just take a moment to fill out the evaluation today, we'll leave this up for the next 20 or 30 minutes, so please feel free to take your time. As I mentioned, the questions that did not get answered, they will be sent to the presenters, and we thank you all for joining us today.